Hello, welcome to this Monday evening stream. We're going to be testing out some neural net coding. Earlier today in the stream, I got distracted doing some neural net coding, and I'm just going to show the result of that. Hey, Destructor, how are you doing tonight? So this is So I was trying to do some sort of neural network field like this before, and I figured out that you can't train it properly because of the time it takes to do the back propagation. But what I did figure out is that, so this green is the target and the purple line down here is this neural net. The red is the neural net right here. The right side here is the output, so because it's all black, the purple line is just flatline, but as soon as this red is going to hit the black part here, the purple line is going to spike up, and you can see here the purple part is all over the place. But what I figured out is it trains just with these random weights in the first layer, and I remember this is like a hidden learning machine where all it is the output layer, and all of this can be thought of as the hidden layers that are just completely random and fixed. So extreme okay. So extreme learning machines are feed-forward neural networks. Feature learning with a single layer or multiple layers where the parameters of hidden nodes, not just the weights, need not be tuned. These hidden nodes can be randomly assigned and never updated, or can be inherited from their ancestors without being changed. In most cases, the output weights of hidden nodes are usually learned in a single step, which essentially amounts to learning a linear model. It is absolutely beautiful method. Now I just need to figure out how to implement something like it. So I figured out this is something like it, where it has a fixed hidden output, hidden layer, and then trains the output layer. That's interesting. There's controversy over it. So anyways, this is this little neural network that I programmed in JavaScript. So I can display it in this little graphic program here. At the moment, it does not train. I was trying to do simple back propagation, and I messed something up with the algorithm, and it doesn't train. If you see here, it just flat lines. The red is the neural net, the green is the target. Let me see, what am I initializing? I'm initializing weights to 0. Sorry, bias to 0. Then I'm initializing weights to like 1e, -2. Forward propagation with clamp 0 to 1. Backward propagation. Training with random values. Scaled by this random amount here. And what am I doing for the training here? Difference equals that. Train if average count bigger than 20. Loss, A loss divided by 20. Average loss smaller than L loss. Oh, and I'm sampling it randomly. Alright, so I'm training this with 1,000 iterations. I'm wondering 10,000 iterations. Okay, it trains. So I lied. I actually haven't ran this code for like a month. So I guess it does train the network. It just takes like 10,000 iterations. And you know what? It doesn't always train it. You can see here. Messed up. Oh, I'm also getting the minimum neural network here. So it finds the best one. So I should be running it like this instead. Yeah, and that's a lot better. But still, it has a lot to learn. It's not doing very good right there. There has to be, I'm looking at improving this, is basically what I'm looking at. So what attracted me about this method here is that it basically all trains right away. Like if you just see, it just fits to the function right away. So that's what I'm looking at replicating here. So I'm going to try doing that same thing where I initialize the random weights with fixed biases and weights, and then only train the hidden or the output layer. So looking at this right here, if I set this to L1 minus 1, it'll only train the output layer. And then I'm going to initialize the biases randomly. Initialize the weights more randomly as well. All right, so it's not training at all. So that's kind of expected. I probably made a mistake. Yeah, so instead of doing random here, I should just do fixed training rate. No, that's still not. Okay, so instead of initializing, so I'm only initializing 2 hidden neurons, so the odds of those neurons' weights and biases actually being what I want them to be, or what will solve this triangle wave, is very low. So what I'm going to do instead is I'm going to manually initialize them and just check and see if it trains even when it has the perfectly correct. So here's the other part to explain. Our green function here that we're trying to approximate with the neural network is just a triangle wave. X times 2, x is the input, minus max 0, x times 4 minus 2. So basically, x times 2 goes up to 1 at the halfway point. Then, once it's at the halfway point, this max 0, x times 4 minus 2, this starts going up at the halfway point, which we subtract, so that's what sends the line back down. This can actually be thought of as a small neural network where it has the input x with the weight 2, and then a neuron with the rectifier linear unit, max 0, with the input weight 4 and bias of negative 2. So this is why I'm using this function as my test, is because the function is actually can be thought of as a neural network. And from my experience, like with this test before, it's very slow to train the triangle wave. It takes like 100,000 iterations. So that's why I think it's such a good test. It's because it's actually difficult for the neural network. So knowing that this is a neural network, we can fill in the first weights and biases manually by going biases. Let me just make sure I understand how this is working. So this is an array. Yeah, okay, so the biases and weights are each their own array. So this is the first hidden layer's first bias. We want this to be 0. Then we're going to fill in the weight. So the first weight we want to be 2. Now the second bias we want to be negative 2. And then the second weight we want to be 4. All right, so now we know that the first layer actually has the correct weights. So without doing any training or anything, I'm just going to output this. Oh, wait. Yeah, so the weight is 1e negative 2. This should probably I should probably scale these random weights by the size of the neural net layer. so that it on average adds up to being 1 and is normal. So let's see if these are inputs for L size. Then we probably want 1 or 2 divided by L size. So this is the other thing I love about JavaScript, is I can actually debug this super easily by just doing console.log nn, and it'll output to the console all the neural net values. So I can go and see what it's initialized. So it's initializing to not a number. Okay, I messed something seriously up. What did I mess up here? Random times scale. Scale equals 2.0 divided by L size. It's LZ instead of LSZ. Oops. Okay. So interesting. Very interesting. Now we can see this at the halfway point is our first times 2 minus 1. And this is what's supposed to be pushing it downward, but because all the weights initialize positive, so the real test of this will be seeing if the training can pull this weight up and push this down. So I'm going to try putting it through 100 iterations. And I'm going to try doing a fixed learning rate. Doing loss here, I'm just going to do like 0.2. And instead of doing random here, I think I'm going to do constant training. So instead of randomly sampling values, it's just going to constantly loop through them. All right, so it's not learning to push this down, but it is learning to pull this up, which is really interesting. Let's see after 10,000. No, yeah, so it's only learning to pull this up. It's not learning to push the other one down. It's actually really interesting. So this is kind of what I was afraid of, or not really afraid of, but I kind of thought that the neural net backpropagation wouldn't be able to learn to get through that bump. So let's see what the weights. Yeah, so the weights here are supposed to be, this one is supposed to be pushed to negative, but it's not. And for some reason, this one's being pushed super low instead of the other one. So the interesting thing about that extreme learning machine article was it discussed training the neural net in one go on a linear model, which isn't that. Maybe this maximum right here is the issue. I don't know. Training it in one go, which might actually be good. Oh no, yeah, so removing that clamp made it even worse. It's the input times the derivative. Yeah, so it is not learning well at all. So I need a different method of doing this. I don't know. So this is supposed to be pulling down negative. Let's see, the backward part, or actually this part right here, the target minus the output sine waves can it learn? Maybe. I've actually broken it right now because I'm trying to test just training the output layer and not training the hidden layers or anything. I think what I'm going to have to do is do the same thing that I did right here, where I seed it with a random amount. But yeah, that still doesn't work. Really interesting. So let me actually see what's it training to. Let me disable this and the code that's making it only train the output layer, and then let me test. What is going on right here? I feel like something's going wrong right there. I don't know what it could be though. Isn't it supposed to be random just at the start of learning? It is. But yeah, I was trying it with a fixed hidden layer. Gain loss times 0.2 plus random. Yeah, I don't know. I guess maybe the random does actually work better here. No, it didn't. What the heck? I'm wondering if there's some sort of bug with this, because that looks ridiculous. Let me look at these weights. Oh yeah, so it's kind of learning it. But what the heck? Why is it doing this? Okay, that looks pretty good. Biases 2.5, weight of negative. Wait. Why does this have positive biases? How the heck? Oh, it's inverted. Man, neural nets are freaking confusing. Let's see if we can improve this training at all. I think I might try doing dropout, where I only train on half of the samples at once and randomly drop out half. But yeah, I swear this should be able to train the single layer. It shouldn't get stuck like this. I'm kind of determined to figure out how to get this working. I can try it on a sine wave now, just to test it out here. Let me just uncomment this, or comment it. All I need to do is change this to a sine wave. So sine x times 0.5 plus 0.5 times pi times 2. All right, so that's the neural net's approximation of it. To make it better, I need to add more hidden neurons. So there you can see with a few hidden neurons, it gets it pretty well. But like, I still think this training can be improved. Like, it's doing 100,000 iterations here, and it's not even training to that good accuracy. I really think it can be better. But the whole thing with neural nets is you just increase the neurons like this, and it should get better. It actually just got worse there. I think the randomness here is to blame. Kind of. All right, one second. Let me see. What does this neural net look like when it doesn't have any training? Okay, that looks all right. It's adding up to 1. This is weird how even with the 64 neurons, it's not, maybe it has too many neurons. Maybe there's too many. No, apparently it needs the random seeding. Or actually, maybe it needs different training rates. So the training rate I'm using right now is multiplying by the loss, so the training rate scales down over time. So let me try some other training rates. Maybe a bigger training rate. Oh, that actually seemed to work better. Yeah, so like that's so weird how it's just training on 1/2. So yeah, I'm gonna try adding dropout to this. Okay, so what's the initial learning rate? It's 1 times 0.5, so it's 0.5. Before I was training it at 0.2. But so if I'm going to sample these points randomly, what I need to do is generate an array of samples. 0.5 is so big. Yeah, I know. I saw someone train their neural net on 3 learning rate. I've never seen someone use above 1 before. But they trained a digit classification on 3. Okay, so we're going to do a fixed number of samples. 10. So then what we're going to do is, how are we going to do this? Zero 0.01. Yeah, 0.01 is pretty common. I'm going to copy this part up here, I think. Then I'm going to set average C to samples.length to begin. Okay, so then this is going to check if average C equals samples.length. Calculates the average loss by doing a loss. I'm going to need to set this up then as some really high number. Divided by samples.length. Then I should clamp this at 1 as well. Okay, then I need to generate my samples. So what you do for this? Okay, so this is actually the part that I don't know how I want to do. I think I might initialize it as an empty array like this. And then I'm going to have a variable called nSamples, which is going to be 10. Okay, so I need to initialize the samples array with these values. So I divided by nSamples minus 1. So that'll fill it up with the values from 0 to 1. Then straight away, I need to knock out half of those samples. So actually, I need to do samples times 2. N2 scale equals 1 divided by N2 minus 1. Okay, so this will automatically scale it. Then the dropout part is automatically removing half of these randomly. So I'm just going to do samples.splice random samples.length. All right, so that just removes random half of the samples. Apparently this makes training more efficient. Apparently I should also do this as batches. So what I should be doing is apparently adding up the changes to the weights and biases. But that's something else to test afterwards. We'll just try it like this first. I'm actually going to try it without dropout first. So then, now that we have our samples, when we do X, if we want to get a sample, we do sample ID equals random times. It's basically random samples picking out of a hat. So floor this as well. I've got floor. All right, so then to get our X, we do samples SID, and then we remove that samples. We remove that sample like this with splice. Oops. So actually, I think instead of doing this average C counter here, we can just do if samples.length equals 0. And that should do it. Train backward. Loss of 0.5. Yeah, I'm going to try 0.01. All right. Let's try training this. There's something wrong with it because it froze the browser. Oh no. Oh no. So you are making like a neural network framework that can train on any type of data with modifiable count of hidden layers and neurons with them. I'm testing it. Not sure if I've actually made one yet. Oh my god, it deleted the code. Jesus Christ. Hold on. I actually saved that because I kind of expected that to happen when it crashed. Oh man, that's good. That's good. This is why you don't program things in a web browser that can crash all the time. All right, so now we're back like 30 minutes ago. So I'm going to need to just reprogram all of that dropout stuff, and I'm going to make use of this save button. All right, so I'm going to do a sine wave, just like before. I'll do 100,000 training steps. All right, and I'm going to change this to use samples. So samples equals 11. Samples.length equals 0. Yeah, so I'm just gonna quickly program this stuff. This is a good time to put music on. A web page is slowing down your browser. What would you like to do? Is it still slowing down? I closed it though. Holy shit! What is using 20% of my CPU? Jesus Christ. Let me save this. Let me just close everything. What was even happening there? That wasn't Math Canvas, was it? I actually don't know what was happening there. Was that YouTube? It's YouTube. Why is YouTube using 25% of my CPU usage? What the balls? Man, what the hell is happening with the internet these days? Praise the sun. Alright, take out this random part. Just do times 0. Okay, so now I actually didn't make that many changes, so all I need to do now is just add dropout. Or I'm not even doing dropout yet, I'm just doing random samples. So our samples are 0. We basically do the same thing as here. Divide by the number of samples to get the average loss. Copy that neural network if it's the minimum loss. It's pretty loud. Alright, then we create our new samples. samples push I divided by or times scale. Alright, there we go. So then sample ID equals samples.length, or random times samples.length minus epsilon, so that it doesn't go above the length. Then x is samples SID, and then we remove that samples, or sample. Okay, now we're back where we were before. Let's save. Is there a way to save over or rename this so it doesn't keep saving it as number 1, 2? I guess not, eh? Whatever. Alright, so if this is anything like before, it's going to crash. So I'm just curious what would make this crash? X is undefined. X is right here. I don't think it's right here either. Let's see, places where it looks for X. Oh god. So this doesn't match up with the search. That's crappy. The plight of doing custom highlighting in HTML and CSS is that you have to override every single scrolling thing or anything, or it doesn't match up. Oh my god. That's bad. Well, that's another thing to fix. Where is X undefined, though? If I can't search through this here... Oh, that's supposed to be floored. NS0 is undefined. What? It shouldn't be. Oh, I'm overwriting it right here. And I froze it again. God damn it. What is even happening? Oh my god, refreshing the page doesn't even fix it. Holy crap. Man, I kind of hate web browsers like Firefox. Like, the more I'm using them and the more they're crashing, holy shit, it's annoying. I keep saying this and then I don't go back to native programming. I don't know what's wrong with me. Oh, I'm setting I in here. Trained to a loss of 0. No, it didn't. That's a lie. That is a complete lie. I just didn't initialize a loss. To a loss of 0.4. Now that's accurate. Okay, so it isn't training at all right here. That's interesting. And this is what the neural net stop making it crash then, lol. See, I can't really help that because any for loop or anything that just goes forever crashes it. And when you're doing neural nets, there's lots of for loops. All right, so it's setting the scale way too high. Random equals times scale, or equals random times scale. Scale is 1 divided by LZ. I have no idea why this is so high and so low. It's either all the way up or all the way down. Okay, what is happening here? Not training, is it? Oh, I guess it is training in that one step. All right, the training rate is definitely way too high at 0.2. I'll try 0.01 training rate. All right, something's definitely messed up there. Because even with this one iteration, it's either clamping it to the floor, sending it straight up. Oh my god, it's because I'm doing it randomly. That explains it. There was way too much random generation. Okay, so now let's get back to testing this. 10,000 iterations. That actually didn't train that bad. I don't know why it didn't train at all right here, though. Like, why is it skipping this whole area right here? So what's really interesting is it's doing it every single time. It's skipping the same area. I actually don't know what's going on there. Try doing 100 neurons. 100,000 iterations. So it actually takes a while to train now. And it's still missing this part right here. That's so interesting how it gets the downward slope, but it doesn't get the upward slope. Oh my god. So let me try training it by loss. Oh, I'm not clamping the loss, so it's insanely high at the beginning. This is supposed to be min 1. It's actually not horrible at training right now. So it's better with a higher or lower learning rate. Well, it's actually way better with higher. Let's see if it's good with a bit of randomness. Oh yeah, the bit of randomness actually helps a ton. So that's actually training pretty... it's better, but it's still pretty bad. So now I'm going to try adding dropout, where I do twice the number of samples and then I delete half them. So that loop right there will loop through and delete half the samples. I'm going to save this just in case. Oh my god, it actually trains way better. That's pretty cool. Let's see if ramping up the number of neurons helps. It's still not training perfectly. Let's see. After I want a method, I want to get this going so that, oh my god, that's actually working really well. I want to get this going so that if you train it with 100,000 iterations, it'll eventually converge. And that seems to be what I've got right now. I'm actually pretty happy with this. Because even after 10,000 iterations, it's still pretty decent. Let's try our good old triangle wave now, and let's see how much of an issue it has with this. Yeah, so it definitely does better with more neurons. I still think I can train better than this. So that's what I'm going to try to do. I'm going to tweak these hyperparameters. I'm also thinking I should train one layer, somewhat layer with more of a learning rate than the other. So that's definitely too much random. So interesting. You need like just the right amount. Loss times loss right there seems pretty good. I still want to get it able to train though with like 2 neurons. Like I know that the triangle wave is actually just 2 neurons right there. So I want to be able to get these 2 neurons to match it. that seems to give the best consistent result right here. We're very close to the finish. I'm also thinking I might increase this learning rate for the output layer or the hidden layer. I'm not sure. So what I'm going to do is I'm going to set these variables here, and at first I'm going to try doing divided by k plus 1. So this will train the output layer with less. It's hard to tell if that's better or worse. So we'll run it a bunch of times. Still trains a whole bunch of times without converging, which is pretty bad. So instead I'll try doing it backwards. Do L minus K, or L1 minus K. Wait, let me just calculate this. This might be wrong. Okay, nope, that should be good. So this trains the output with more. That actually seems to be worse than the other method. I just went back. God damn it. I'm getting tired. Yeah, I swear though, this triangle wave is actually harder to train to than the sine wave. What could I do to improve this training? I don't think separating training one layer faster than the other will actually help, but I don't know. I wish I even knew what you were doing. I don't even know what I'm doing. Yeah, I think this works worse. I'm going to start going and testing the extreme learning again, because that's the one thing I want to see if I can train the linear model on fixed hidden neurons, because that would be really, really good. Basically have a guaranteed training. It's interesting how this needs the randomness. This is what is attracting me towards the extreme learning, is even this needs to be seeded by the random values. Train. Basically, though, I'm trying to get the neural network, which is this red line, to match up with this green line, which is the triangle waiver target. And right now, I can get it to match up. If I set this to like 1,000,000, If you see here, it matches up like completely perfectly, but I don't like this because it's so slow. Like, I'm actually thinking that this is, like, if you see it doesn't even train perfectly at like a million iterations, it still has that little bit of error. So I'm just like, there needs to be a better way, which is why I'm going to look into the extreme learning. And I still have one more thing I want to try. What if I just scale these randomly? What if instead of scaling randomly, instead of seeding with random values, I just scale it randomly? No, that didn't work that well. Yeah, this isn't looking very good. Scaling it randomly doesn't work either. In fact, it actually makes it worse. All right, I'm going to go get some water, and then I'm going to try doing the extreme learning again, training with a fixed hidden layer. I'll be right back. All right. So I'm going to initialize do what I did before and manually initialize the neural net. So we know our first bias should be 2. Or actually, our first weight should be 2. Our first bias should be 0. You know what? Let me just make sure this actually works the way I think it works. So then if we set the other bias to -2 and the weight to 4, and then we want the first bias of the second layer to be 0. We want this first weight to be 1, and we want this second weight to be -1. What does this look like? Okay. Times 4 minus 2. Oh, so we actually want this to be -1 times 2, and then this to be times 2. Maybe times 1. There we go. Okay, so this is what we want it to train to. We want it to train to a bias of 0, a weight of 1, and another weight of -1. So obviously the back propagation doesn't come to that result from what we tested before. Thinking about it, it's pretty obvious actually why it happens is, first of all, the bias gets pushed up. And you know what? This is one of the things I'm thinking about this hidden learning machine now, is it shouldn't have a bias. It's not going to actually, I'm not actually going to train the output layer's bias. It's just the weights. And then when it's trying to train these, because these are basically equal and symmetric, they actually repel each other, I guess would be a way to say it, or when it's training, they interfere. All right, so what I'm going to try to do now is I'm going to try to train this without back propagation, knowing that the layer is perfect. I know that all I need to do is train the output layers. So comment out this perfect output layer. So what I'm going to do is I'm just going to loop through the number of samples. I'm wondering if this needs to be normalized. I don't know, we'll just try it. So what I'm going to do is I'm going to initialize these weights and biases to 0. And then I'm just going to add them. I'm just going to, since it's a linear model, I'm just going to do it as a sum. So I'm going to do a very similar thing that we do here. Instead of randomly sampling, we're going to sample it fixed. I divide by n samples minus 1. We're just going to do one loop around the whole training data. So we'll do the forward propagation. Then instead of calculating the difference, we're going to get the target. And then we're going to sum the target times the output values to get the weights, or hopefully get the weights is what I'm going to try to do. So I'm going to comment this out. Or actually just delete it. So I'm just writing all of this hard-coded just for testing. This isn't actually going to work as a for all neural nets. I'm just testing it for this specific neural net. This would be weights 0 plus equals I think it's NS1. Okay, like that, probably. Times the target output, which is TY. So then when we're done here, we're going to loop through and we're going to divide the weights by the number of samples. Train to a loss of 1. Okay, so it did not train. Console.log, neuralnet, let's see what it trained to. Curious what it trained the weights to. .381, 0.072. Divide equals n samples. I feel like this is wrong. Let me experiment with that. That's way too high. Yeah, and it's not getting the negative either. So yeah, I think this is where you need singular vector decomposition. Which is really hard. Or there's a bunch of different ways to do it. And it's kind of just like the neural net backpropagation where you're not guaranteed to get a result. So that's not a good solution. What's the difference between this and the things that learn to play video games? The things that learn to play video games have like way more neurons, and they're probably way better programmed than this. Or I almost guarantee they're way better programmed. Alright, so if this needs to learn negatives, this YouTuber I watch, he used a language called processing or something like that. Yep, there's popular machine learning language. Yeah, it's crazy that there's languages just for machine learning now. I wonder if I should just do this iterative just like this, where I just calculate the difference. There are people at my work going back to school after like 10 years to learn it. Man, I don't know how I feel about that because I don't think we're actually that far along in like machine learning yet. Like, I'm gonna be real with you, it's not that useful. It's like it's really slow. I was hoping to use like machine learning for a whole bunch of things. Like, it's really too slow to do for a lot of real-time stuff, like with games, which is what I really wanted to use it for. But yeah, the ones that play games seem to be doing well. Yeah, there's actually been a bunch of papers talking about how using games as judges is actually really bad because it has a whole bunch of human biases built into it. That's the exact stuff we're trying to get AI to beat. But yeah, all the stuff with AI playing games is open AI is really interesting. Oh man. So I need to somehow get one of these weights going negative when the target's supposed to be going down. So maybe I do have to do this recursively. Maybe I will try doing it recursively. The big GPT-2 language model. Nope. Ooh. We've trained, oh man, this text is horrible. We've trained a large-scale unsupervised language model which generates coherent paragraphs of text, achieves state-of-the-art performance on many language modeling benchmarks, and performs rudimentary reading comprehension, machine translation, question answering, summarization, all without task-specific training. Oh my god. Was trained simply to predict the next word in 40 gigs of internet text. Holy shit. We are not releasing it. Oh, that's really interesting. Transformer-based language model with 1.5 billion parameters. Holy. I swear to God, machine learning is really just throwing giant numbers of neurons at things. I vortex the NIM. You're right, Destructor. Well, if I ever need data for my neural nets, I know who to ask. They actually used articles linked from Reddit. Ooh, interesting. So what I'm going to do here is instead of training on the exact target, let's see examples. I think I've already seen it actually posted around. I started reading it and I was like, I think I've seen this before. I'm going to get off the computer soon, so I kind of want to see if this is going to work. There's one thing I want to try with this too, which is using the error back propagation or just training with the derivative right here. So multiplying these input states by the derivative. I'm wondering if I should be subtracting the weight results from this as it goes. I don't know. We'll see. Oh my god, it actually trained. Holy shit. It's actually training. Oh, fuck yeah. Do you see this? Do you see this? This is extreme learning. 100 iterations and trained perfectly. Oh my god, that's awesome. Okay, so now the reason why this trade's so good is because our hidden layer is already completely optimized for the task. But what I'm going to do is I'm going to initialize the hidden layer now. Actually, I should initialize it right here. So random times 2 minus 1, then weights times 2 minus 1. So this is the really difficult part, is weights are going to be well above 1. So randomly generating the weights for this would be really difficult. I wonder if I can apply the same learning to hear somehow. So as the weight goes up, the biases also go up. Yeah, so there's still definitely lots of stuff to improve with this. Like, it's not going to train well randomly generating these. So is there a way that I could randomly generate them or figure out what sort of weights it's supposed to be? So like the issue is this needs a weight of ×2 to make it go up to here, but there's some things that will need a weight of like ×100 to bring them up right here, or like ×10 to bring them up like right here on the graph. And the issue is the higher you increase that random generation range is the more, basically the bigger range you have, the less odds you have of hitting the area where you want it to be. Like you want it to be as close to this like ×2 1 bias as possible. So I'm actually thinking this is going to be very simple or very similar to this uniform sampling that you want for ray tracing, where you're trying to do uniform points that are randomly sampled across a big range. So you know what? Let me try this. So how am I going to do this that these are going to be scaled correctly? I don't even think I need negative weights because it'll train negative weights on the last step. Yeah, I could probably get away with actually just doing this as like ×4. All right, so I got to think about this. If I want to generate the optimal hidden layer, I'm not going to worry about any uniform distribution here. I'm just going to do it randomly. But if I wanted to uniformly distribute them, so I know I need biases to go from like 1 to -1. But weights, I think I can do is just positive. See, I don't know about that because there's some things actually where it'll need to subtract. So you know what? I lied about that. And then there's the other thing of do you even want these neurons to add up well above 1? Like if you do ×4 for every single one of these, but it's connecting to 100 things, and all of those are like above 0.1, it's just going to be like well above 1, which is really bad. You don't want that. You want to actually be like in the middle point. If your values are way too high, it's going to cause issues. So I need to somehow apply this scaling here. While still keeping it relative. So I'm just going to do the bias as -1 to 1. The weights, I'm still going to scale them. But I'm going to scale them by like 5, I think, like this. Alright, so just to see what this looks like, randomly initialized. Yeah, so these are pretty random initializations. They're either way too low or way too high. I'm still wondering if I can make these better. Or at least if I increase this count. Oh yeah, so that's actually not horrible. Alright, so now I just need to adapt this code from before that only trains two neurons. I now need to train 32. I'm actually just going to get it to sample that, which is layer size 1. So right away, we're going to set all those to 0. Just initialize these to 0. I'm going to try just one iteration around the sample data to begin. So then here, once again, we loop through. We add the state output times value we want. Okay. All right. So it initialized as completely blank or flatlined. Wonder if I did something wrong. Try doing 10 iterations now. All right, so that's interesting. It's training with giant spikes here. If we output the neural net, let's see. What is it outputting? What are the biases like? So the biases are all over the place. The weights are between -5 and 5, which is what I was going for. So then these are the trained weights right here, which a bunch of them have ended up as 0, interestingly enough. Which makes me wonder. Well, I can just try increasing the iterations. Alright, so it's really overtraining right here. So I'm wondering if I need to do a lower learning rate or something like that. Oh my god, that's exactly it. How did I miss that? So what's a good learning rate that's not too high and not too low? I think maybe 0.2 or 0.1. I don't know. We'll see. Okay, well that works in 10,000 iterations, so that's still better. Let's see if we can get it down to 1,000 with a different learning rate. If lower or higher works better. I'm thinking what I actually need to do is scale this down over time. So let me try doing divided by I. Yeah, so you can actually see it going down right there. That's not good. That's better. Maybe if I record the loss, I don't know. Because I understand how doing a constant amount of like 0.5 here causes it to overfit a whole bunch right here. But I also understand how setting it to a low value like this causes it to not completely fit. There should still be a better way of training this. I don't know. Let me see. I'm honestly pretty happy with the stuff I've done tonight, though. I got the training for the normal neural network much improved using dropout. I actually didn't realize that just using dropout would give that much of an improvement. That's pretty cool. It's just a way of sampling, which is super interesting. And I'm already happy learning that I can just train the last layer like this with enough hidden neurons. That's really cool. The one thing that I'm just curious about is training it even better now. And then possibly, because if you see here, you can optimize this much further, I think. Like if you look at the weights, all the connecting weights here, you could cut off all these weights that are 0. And I think you can also cut off the weights that are like very close to 0 like this. So you could actually cut down the neurons on this network by a giant amount. And I think a bunch of these neurons actually offset each other and interfere with each other. But that's complicated. I don't know how I would detect that. Okay, I'm just going to look at another way of training now. So I'm going to loop through. I'm going to loop through differently. So this is training each sample. But what I also want, that just deleted the code. God damn it. Are you kidding me? That actually just deleted the code. For fuck's sake. Oh my god. I gotta stop editing stuff in the browser here. I gotta start writing native code in a proper editor. Because that is just stupid of me. That'll probably be the end now, because I'm not going to bother rewriting that. I already figured out most of what I need to learn. The one last thing is like final training methods. The one thing I was going to try was, first of all, measuring the loss and then scaling down the training rate by the loss. And then another thing I was going to mess with was actually only training the point of maximum loss here. So like these points here where it's maximum, it would train here. But I actually think that would be worse because there's no reason not for it to train at these parts right here. Anyways, I think that was a pretty productive neural net stream. I love testing neural nets. It's fucking dark now. You can't see me at all, but I had fun. I hope everyone else had fun watching this. Yeah, I'll be streaming again tomorrow if you want to watch that. If not, I'll be in Discord talking about more of this stuff. Thank you for watching. Okay, I don't know what's going on with OBS, but it's not detecting the proper window. Like I go to my ending thanks for watching screen, and for some reason it detects the different window that has a different name. It's actually ridiculous, but can't change that. Whatever. Thanks for watching. Bye-bye.